For this session, we're going to be talking about improper integrals. Improper integrals are when infinity is involved. So let me give a few basic notes on this and then we'll look at some examples. Let's look at what it means to have infinity involved. If I had this graph and I wanted to know the area under this curve from, let's say, A all the way down forever. So I wanted this area. So the question is, as x gets larger and larger and larger, does this area start to approach a certain value? I hope that that kind of rings a bell in our discussions in the very first part of this class about a limit. Limits are, does the function approach a value as you approach infinity or approach another number? And in this case, as you can see, if I were to extend the x-axis out, and I meant for that to look like it was just hitting above the x-axis, is that this graph is getting closer and closer to 0. So the area up to this point is not much more than the area up to C and is not much more to the area up to D. So at some point we can kind of call it a day and say our area is going to be very close to this number. This graph is said to be convergent. And that means if something is convergent, that there is a limit, and therefore we will be able to estimate the area. If we were to have a graph that looks something like this, and I wanted to know the area from A to infinity, then my area, as you can see, starts to grow and grow and grow. Even if I just went one more step from B to C, look at how much more area we would have to add on. This type of graph is called a divergent graph, which means that there is no limit, and therefore the area under the curve is just getting infinitely large. So when we are looking at improper integrals and we are taking the integral of something that involves infinity, we're going to have to be using the concept of a limit. So let's refresh ourselves a little bit about the concept of a limit. So REM stands for remember. The limit as B goes to infinity of 1 over anything to a power equals 0. So the limit as B goes to infinity of 1 over B squared, that's 0, of 1 over B cubed, that's 0, just 1 over B, that is also 0. Because as the denominator gets larger and larger and larger, the value of 1 divided by that denominator will get smaller and smaller and smaller, and it will get closer to 0. So our goal is going to be to look at what happens as things goes to infinity. There are 3 types of improper integrals. One where we go just to infinity, one where we might go to negative infinity, and one where we start from negative infinity and go to infinity. So let's do an example of each of those. So the limit of from 1 to infinity of dx over x. This is the same as 1 to infinity of 1 over x dx. And so you should be able to integrate this. When you integrate this, you get the ln of x, and we have to integrate that from 1 to infinity. And so the question is, well, how do we integrate that from 1 to infinity? What we do is we take the limit as b goes to infinity and we evaluate from 1 to b. So in other words, I'm going to plug b in and I'm going to plug 1 in just like we did in the last sections of definite integrals, but then I'm going to say b is going to infinity. So let's do that. The limit as b goes to infinity. So as we get closer and closer to infinity, does our graph area look to converge? And so we do the ln of b minus the ln of 1. And the ln of 1 means e to what power gives me 1, and that would be 0. So that's 0. And I'm just left with the ln of b and the limit of that as b goes to infinity. And depending on how comfortable you are with this stuff, you might want to look at your table of values and watch what happens. But what we can do is talk about it numerically as well. Remember, the ln of b is asking us e to what power gives me b. That's what it's asking. So if b is getting bigger and bigger and bigger, then the power that e has to have is just going to get bigger and bigger and bigger. So there is no limit for the ln of b, which means that the original function is divergent and the area is growing without bound. So if you're going, oh my gosh, I don't remember limits, I'd encourage you to go back all the way to Unit 1 and review the concepts of limits, especially the ones the limit as you go to infinity. Let me do a second example. Where we are starting at negative infinity. So from negative infinity to negative 2 of 1 over x squared dx. And so let's integrate. Remember, this is the same as the integral from, and let's make this from a to negative 2 of x to the negative 2 dx. And so we're going to, when we take the integral, we're going to have to take the limit as a goes to negative infinity, because we replace negative infinity with a. The integral of x to the negative 2 is x negative 1 over x to the first, because it would be x to the negative 1, so we have to put that in the bottom. And we're going to evaluate that from a to negative 2. So first, remember, we're going to plug in negative 2. So it would be negative 1 over negative 2 minus negative 1 over a. And if we clean that up, the limit as a goes to negative infinity, we get 1/2 plus 1 over a. Remember, when you have a sum or difference, you take the limit of each piece. So the limit of 1/2 is 1/2, because the limit of a constant is a constant. And the limit of 1 over a, as a is getting very, very large negatively, would go to 0. And so 1/2 plus 0 is 1/2. So 1/2 is the estimated area under the curve if you start at negative 2 and go down to negative infinity. Now let's do one example where we go all the way across the spectrum. The integral from negative infinity to infinity. Let me back up just 1 second. We would say that this was convergent, because if it's convergent, you have the convergent is because you had the limit, you were able to find the area. So let's now do 4e to the negative 3x dx from negative infinity to infinity. What we're going to have to do, because we can't take two limits at a time, is that we're going to have to break this up. And so we just pick a number, and I like to pick 0 because 0 often makes things go away. So I'm going to go from negative infinity to 0, and then I'm going to pick back up at 0 and go to infinity. So we're going to take the limit as we either go to negative infinity or to infinity. So when we integrate 4e to the negative 3x, we get negative 4e to the negative 3x over 3. We have to evaluate that from a to 0, and we have to take the limit as a goes to negative infinity. For the other piece, the integration will be the same, but now we're going to start from 0 and go to b, and we'll have to take the limit as b goes to infinity. So you cannot run them both at the same time, so you have to split that up. So now let's do some plugging in. Limit as a goes to negative infinity of negative 4e to the negative 3 times 0 all over 3 minus negative 4e to the negative 3a all over 3. Let's see if I can make this all fit on one line. And then the limit as b goes to positive infinity, we're going to have negative 4e to the negative 3b over 3 minus negative 4e to the negative 3 times 0 all over 3. And now let's clean that up a bit. So we have the limit. And I sometimes get lazy and don't write the limit thing until the end. Negative 3 times 0 is 0, and anything to the 0 is 1. So e to the 0 is 1. We're just left with negative 4/3. Two negatives here make a positive, and so we have 4. Now the e to the 3a is a negative exponent. I'm going to write that in the bottom to make it a positive. So e to the 3a, this negative exponent moves it to the bottom. Over here, the limit as b goes to infinity of, again, that negative 3b would be in the bottom, so let's move that down. And two negatives make a positive. E to the 0 is 1, so we're going to have just 4/3. And now let's take a look at the pieces. I'm going to do the easy ones first, and those are our constants. So the limit of negative 4/3 as a goes to negative infinity is negative 4/3. The limit of positive 4/3 as b goes to infinity is positive 4/3. Now let's take a look at these other ones. I'm going to do the easiest first, and I think that's the one over here. Let's think about what happens to this power as b gets bigger and bigger and bigger. So we take bigger and bigger numbers, we multiply it by 3. That gets bigger and bigger and bigger. So this power is just getting huge. And then we're raising e to that power. So we're taking a base of approximately 2 point something, and we're raising it to this huge power. This number is getting huge. And then we're tripling it. So the denominator of this fraction is getting gigantic. The negative 4 on top isn't changing. And negative 4 divided by a bigger and bigger and bigger number is going to go to 0. This is the same as negative 4 times 1 over, or we can even pull the 3 out. We could write it like that. And 1 over anything to a power, the limit of that is 0. Alright, but let's talk about this other one. 3a is my power, but we're getting closer and closer and closer to negative infinity. So when I plug a negative power in here, that technically is going to move it back up top. And now this thing is getting huge up top. Over on the red one, it was getting huge down bottom. But because of the negative infinity, this power right here becomes negative. We can move it back up top. It's getting huge on top. We're then multiplying it by 4. That just makes it bigger. We're dividing it by 3, but that just slows it down just a little bit. But this guy is cruising out of control. This piece right here does not have a limit. It's an infinite limit. It's going to keep on growing. So whether we add or subtract anything to it, but these actually cancel, and then we have 0, we're left with infinity. We have ourselves a divergent function, and therefore the area is growing without bound. What I encourage you to do is to graph these functions on your calculator and look to see, is it a graph that converges, meaning it approaches, doesn't have to be the x-axis, but it approaches a number, or is it divergent where it's going out of control? And that might help you confirm if you get a number answer, it should look like the one on the left. If you get an infinity or no limit answer, it should look like one on the right. So just be real careful on taking your limits as you find the integrals of functions that are approaching infinity.